I continue to read the book Genesis, The Story of How Everything Began by Gildor Tonelli. This is an introduction and the second section, A Dangerous Voyage. In order to understand the origins of our universe, we must be prepared to undertake a risky journey. The danger comes from the fact that we need to push our minds into areas or environments so remote from those we are accustomed to that our usual conceptual categories are no longer of any use. We find ourselves obliged to say the unsayable, to depict the unimaginable, to experience the limits of our mind. Limits of a mind that for Homo sapiens has been a powerful tool for exploring and colonizing our planet, but which turns out to be altogether inadequate for fully understanding what happens in such vastly distant places. Like the explorers of old, we have no other option but to point the prow of the ship towards a horizon, and to accept the risks and the unknowns that go with navigating in uncharted waters. Similarly, in scientific research, the voyage home and return to port is also very important. In this respect, the modern researcher is a lot like Ulysses, for wherever his journey takes him, he's always dreaming of the moment when he will reach Attica again. Coming home also means, even if no new territory has been discovered, or we have suffered a terrible shipwreck, that it is possible to warn other sailors about the routes not worth taking and the dangerous passages that should be avoided. We do this because modern science is also a great collective adventure. We have theories and charts to guide us, but the chance often takes us to places that are completely unknown. We have ships that are meticulously cared for, but we only need to neglect one small detail and disaster can befall us. Our crew is a colorful and lively community of thousands of passionate mind, patient and curious modern explorers, quick like Ulysses to invent new stratagems to overcome whatever unexpected events might be thrown at them. Despite the objectives of our research raising almost philosophical questions, what is a matter made of? How did the universe come into being? How will the world end? The practice of experimental physics is one of the most concrete activities imaginable. A particle physicist, one of the thousands of researchers in the world exploring the behavior of the extremely small components of matter, does not spend his time sitting at a desk making calculations, meditating on theory, and fantasizing about new particles. A modern apparatus for high-energy physics is as tall as a 5-story building, weighs as much as a cruise ship, and contains tens of millions of detectors. To construct and make operable these are miracles of technology. Thousands of people are required, and painstaking, obsessively detailed work that can take decades needs to be done. To devise new instruments more sophisticated than the previous ones, to prepare ships more agile and swift for our navigation. We spend years producing prototypes in relentless efforts to make them work before going on to build them on a vast scale. And even when detectors are rigorously cared for and installed in the experiment, functioning quietly for months, we are always faced with the fear of a catastrophe. An overlooked minor detail, a defective chip, a fragile connection, a cooling tube that has been hastily soldered can, at any moment, cause irreparable damage to the entire collective enterprise. The difference between outstanding scientific success and the worst of all possible failures frequently lies hidden in some stupid, insignificant detail or other. The two parts of knowledge. How do we collect experimental information on the birth of space-time? How do scientists study the first cries of the infant universe? Two parts of knowledge come into play here, completely independent and different from each other. On the one hand, there is particle physics, exploring the infinitely small. Its starting point is the matter that surrounds us, what rocks and planets, flowers and stars are made of, along with everything else besides, including ourselves. This matter has very special properties, which may appear ordinary to us, but that are in reality very peculiar and in a way linked to the fact that the universe is a structure that is both very old and currently very old. The most recent data tells us that our home was built almost 14 billion years ago, and that we are talking about an extremely cold environment, reaching what seems like impossibly freezing temperatures. For us, isolated on the planet Earth, everything seems comfortably warm. But as soon as we leave the protective shell of our atmosphere, the thermometer plunges. If we measure the temperature at any point in the vast empty spaces that separate stars or in intergalactic space, the thermometer registers just a few degrees above absolute zero, which is to say minus 270 degrees Celsius. The matter of the current universe, rarefied, extremely ancient, and extremely cold, behaves in a very different way than when it was recently born and existed as an incandescent object of a tremendously high density. In order to understand what happened in those very first instants of life, we needed to be ingenious, to find a way of returning the elementary vestiges of current matter to the extremely high temperatures of those original conditions. We have to make a kind of a journey back in time. This is precisely what happens in particle accelerators. By making protons or electrons collide at a very high energy, we exploit Einstein's equation, energy equals mass times the speed of light squared. The higher the energy of the collision, the higher the local temperature that will be obtained, and the greater the mass of particles that we are able to produce and study. To reach the maximum energies possible, we need truly gigantic equipment, such as the Large Hadron Collider at CERN, that stretches for some 27 kilometers beneath the ground near Geneva. Here, we find that by heating extremely small portions of space to temperatures comparable to those of the primeval universe, extinct particles revive. Those ultra-massive particles that used to populate it and that vanished eons ago, thanks to the accelerators, they re-emerge for an instant from their icy tomb, as if from hibernation, and may be scrutinized in great detail. This is how we discovered the Higgs boson. We brought back to life several handfuls after they had slumbered for 13.8 billion years. Naturally, of course, the much sought-after bosons then immediately disintegrated into lighter particles, but they had left behind telltale traces in our detectors. The images of these special kinds of decay accumulated, and when a moment came when we were certain that the signal as well differentiated from the background, and that the other possible causes of error were under control, we announced the discovery to the world. The exploration of the infinitesimally small and reconstruction of extinct particles, the study of the exotic states of matter that everything was made up of at first. This constitutes one of the two paths available for understanding the very first moment in the life of a space-time. The other requires super telescope, huge instruments for exploring the infinitely large, and it studies stars, galaxies, and clusters of galaxies in an attempt to encompass the entire universe. Here too, we resort to Einstein's equation, in which the speed of light is fixed at approximately 300,000 kilometers per second, extremely high but not infinite speed. Hence, when we observe a very distant object, galaxies that are distant from us but billions of light years appear not as they are now, and it is quite difficult to define what now means, but as they were billions of years ago, when they actually emitted the light that has only just reached us. Looking with super telescopes at very large and very distant objects, it is possible to watch all the principal phases of the information of the universe live, and to collect valuable data about our history. In this way, by observing the first faint signals emitted from the heart of the enormous gas clouds, we can understand how stars are born. We observe the thickening of gas and dust in the rings of a material that orbit around some new celestial body, indicating protoplanetary systems in formation. This is how our sun was born, and how the planets that orbit around it were formed, and it is truly amazing to see it actually happening. Pushing a little further, we can witness the formation of the first galaxies, turbulent objects that sometimes emit enormous quantities of radiation of all water lengths, an unequivocal sign of a traumatic birth. Through the super telescopes, we can ultimately both observe the wonders of the universe and measure some of its properties with unbelievable accuracy. The local distribution of temperature throughout the universe is like a kind of incredibly memory containing eloquent traces of what happened at the very beginning. Extremely small fluctuations in temperature speak of our most remote history in a language that we have managed with time to decode and interpret. But the most awe-inspiring thing of all is that these two paths of knowledge, based on methods so different from each other that they are almost entirely distinct, undertaken and developed by two wholly independent scientific communities, are nevertheless completely coherent with each other. The data gathered from the world of infinitely small elementary particles, and that which pertains to enormous cosmic distances, converge implacably towards the same story of origins. Let me stop here for this episode.